this send and get stuff. So remember what send and get does is it puts a form out for the user. The user puts in a number. It then waits until the user provides an input, and then later it comes back with whatever the user provided. And we do it again. Put out the second form and wait for the answer. So each of those takes a long time to deliver the result. Then we add them all up, and then we make a web page that sends up the answer. And so it's implemented in a way that where it doesn't wait. There's like no waiting threads or anything. It's implemented in kind of a do and forget way, where if you remember, there's this form generated inside this lambda. That was a long time ago. So if you remember how this worked, this code here contains the code to lay out the form. There was a magic URL that was passed into the form that we get in here. And so then the send suspend then has to send the thing off to the browser, and then it has to do other things, and eventually when the answer comes back, a form with the same magic cookie embedded in it somehow, then it has to reawaken and come back in. And you could implement this with a continuation. It would be possible to do this by having, and that's how I described it before. I said there was a hash table somewhere with magic URLs as keys and with continuations as values, so that the continuation then returns back here. But as it turns out, continuations are pretty expensive. That a continuation has to store the entire state of the program. And web programmers are already worried about session state. You always hear web programmers browsing that there's too much session state and it limits the scalability of the application. And session state is just the stuff that the web designer, the web programmer decided to keep around. The continuation keeps around everything, the entire life history of the program. So it's quite a bit bigger. And so they try to avoid having these hefty continuations. So instead, what they actually do store is they programmatically build up what is the future set of actions that needs to be executed. Because the whole life history of the program in this case was not of interest. We're never going to be jumping back. We just want to go forward with this future. And so there is a way of transforming a piece of code, like this piece of code, into an equivalent piece of code that says, do these steps. And that transformation is called the continuation passing style transform. And that's what we're going to talk about for this in the next lecture. So, we want to figure out how to compute like the rest of the computation. And so if we look at and so actually let me look at a simpler situation. Let's say that there was only one of these. In that case, I would have to say that when the web server comes back with the input of the user, in this case we wouldn't want to add it, but let's say we compute the factorial. When the web server comes back with the input of the user, then what are the remaining steps? It's to compute the factorial and to pass it on to set result. That's two actions. You could kind of make a little function that says, do that, attach that function, and not the whole continuation. Attach that function, and you're done. Now here the difficulty is, of course, that we are having another one of these hefty functions. When this one comes back, we have to do this thing, and then we have to put them all together. So let's think of how we can describe that. So we're going to be using this notation of the program with a whole. So instead of doing the set and get that was buried inside here, I'm going to turn it inside out. And I'm going to say the first thing that I need to do is to do the first number thing. And then later on, I have to do more stuff with it. And so I have to, and so this is the description of the added work that needs to be done. It is the first do whatever, this is what's already has been done, and then you have to call this thing, and then you have to do the addition, then you have to call send result. So let's do this again. So now we're going to turn the second send and get here into a transformed with the /k. And so it has the parameter that it somehow needs. And now h2 has this whole, which I'm now rewriting in the same way. And now let's see what we have. So we're now having a function that says do something, and when you're done, then do this next step. And when you're done with both, then you add up the results. So, and what we have here is we have transformed the continuations into straightforward functions. Every function gives to the next function what needs to be done afterwards. Yeah.
So if I'm not wrong, the square, the small square that we see, it's is it a function name?
Oh, it's a variable name. This thing is a variable name.
And
so it's also a variable name. Here I call it the variable name with the box just to make it kind of intuitive. It's because it's the
so it can be anything else.
Oh yes, it can be anything at all. And so of course they're not really called these. They're called x1 and x2 or something. But then I felt it looked less intuitive. So I used the box here to really show. Here's the whole of the program. And so so I wanted to say, we're doing some computation. And so the send and get, of course, has to go out to the web, and then it comes back with an answer. And then when it has the answer, what does it do with the answer? It plugs it in this hole so that later on, this thing still happens. Then the two get added on, and then they get, the answer gets displayed. So this really is the spot where the result needs to be put in to continue. So instead of having an implicit continuation, we're writing the continuation in actual code. Yeah.
But in send and get, right? So once the control goes to the browser, you take the input. The first number is taken, right? It
Yeah.
comes back. And then you see lambda. You're seeing a second.
So now that means that in the browser in the server implementation, it still needs to have some kind of a hash table where the key is some magic cookie. And now the value is no longer a continuation, but it's a plain old function. A function is much cheaper than a continuation. So the whole point of the CPS transform is to rewrite things that are continuations into plain old functions.
But even in this, you're using it twice, right? Send and get. So.
Well, that's why I have to do it with another step. So send and get, the original send and get, the way I envision it, used the continuation. Now I'm going to rewrite it so that it looks more complicated because of these extra parameters, but it has a lighter weight implementation by using functions.
Where was the continuation set in the original send and get?
Well, we didn't see it. It was captured somewhere in the bulk of where you're close to the sending out data to the HTTP channel.
So send and suspend basically this.
Yeah, somewhere in its internals.
Okay.
And so that's how I described it, but the truth is that actually the send suspend stuff does do the CPS rewrite.
Okay.
So it really does what I'm describing. It's not idle theory. It is so much cheaper to do it this way that you want to carry out this transformation.
And send and get k /k.
Yeah.
Will still do extracting binding, converting it to.
Oh, sure. All of that web stuff.
And that's inside the lambda, or?
No, that would be inside the bulk of send and get or send result. I didn't.
And one small
Yeah.
thing. I'm sorry. What's the significance of /k again?
I just call it /k to say that's the continuation. That's the transform of this function. It's just a name.
Okay.
Yeah, there's no particular significance to it. So in this process, one can transform a continuation into straightforward functions. So that sounds like a curious application, but there are many other applications for this technique. And so I'll show another one that's actually maybe a little easier to understand. generally when you have a recursive function, you have this problem that that the stack will grow indefinitely. So when you write fact in the traditional way, where you write define fact n as, if, what is it, if equal n0, 1, and otherwise multiply what is fact minus n1 n. Then when you run this with fact of a large number, then the stack will grow proportional to this number, and that could be potentially expensive. You might say, for fact, what's the big deal? The largest factorial that you can compute is going to be that large. But the other recursive functions that, say you traverse a list, and if the list is long, you can easily have a list with 1 million members in it. If you traverse it every time you have to pay for stack, that's really expensive, and you don't want that. So there's a motivation that you want to be able to eliminate recursion. And so the classical technique for that is called tail recursion elimination. So with the factorial itself, it turns out we can't do that. And the answer, the reason for that is that as we call the factorials, we have all of these intermediate results on the stack, and we can't easily get rid of them. But one can rearrange things slightly. So here I'm using a fact helper function, where I'm having an accumulator as a parameter, and saying n is less than 1, then return the accumulated value. Otherwise, return n by 1 and multiply into the accumulation the value n. So let's have it to see how this works. So fact helper 3.1 would call fact helper 2, and then here we multiply what? The accumulator, which is 1, with the 3, which gives us a 3. And then later we have fact helper 1.6, which multiplies these ones into 6. And now the point is that at the end, at this spot where I call fact helper, I don't have to make a call, but I can actually jump back here without a recursive call, and I simply swap out these two variables. So let's look at it carefully, because this is an important idea. So over here it has two parameters. And so now we look at how these parameters evolve if the call was recursive, say. And now at this point here, I could call the thing with 2, 3, or I could replace these things with 2 and 3, just splat it over the memory, and jump back here without having another runtime stack. That way I would have replaced the recursive call with a jump, with a loop. Now why am I able to do that? I'm able to do that because the recursive call to fact helper is the very, 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 very last thing that happens in the computation. I've done everything else, and the very last thing is fact helper. In fact, I can't do that in the traditional fact, because after I'm done with the call to fact, I have to do another step of work, namely the multiply. So I can't jump here. I have to come back here and do the multiply. Over here, there was nothing else to be done. And so because there's nothing else to be done, I can, instead of making a recursive call, I can go back to the beginning. So the stack does not grow, and this is nice.
But how will the interpreter know that it needs to jump and?
So it's fairly easy to determine whether you have a tail recursive function. What you have to do is you have to simply find out whether the call to itself is the very last thing that happens. You're gonna do this in homework, I'm sorry. So it's possible to do this. You just look at the code, and there's a few rules that says what happens before, what happens, everything else, and it's easy enough to find out what's the last thing that happens. So it's the beginning of an innermost thing. So this thing has no further. So if you look at this thing here, so the rule basically says that if you have an if, you look at the positive and the negative part, and if it's and those are still both still considered the outermost level. But if it is inside an expression, the outermost level is this, and the fact is buried further inside, and that means it's not challenged. But as we will see on Tuesday, by the miracle of continuing the CPS transform, we can take a regular old function, this function here, and transform it into that form. So you can take your regular recursive function, apply this transformation, and get rid of the recursion by making a tail recursive. And that's a very useful application of the CPS transform that you often see. It's not a magic bullet. There are some functions where when you apply the transformation, the code of the function grows exponentially, so that's no good. But there are many situations where it does work.
This isn't called tail recursion, right? Or is it?
This thing is tail recursive because the recursive call is in a tail position.
And then what if?
This one here is not tail recursive.
What if I move n
What if you
for
if you move the multiplication sign out? If the fact got to be here, the multiplication thing, that's the thing that's in your way.
Okay.
The fact is buried inside the multiplication. If you somehow manage to swap these two, it doesn't work, of course, because then it computes something different.
Yeah.
But yeah, and you can kind of see how if you made the right arrangements for saving the intermediate value somewhere, there might be a mechanical way of going from here to here. And as it turns out, that mechanical way is the CPS transform.
So why is it saying recursion in the last position can be replaced?
Because it's the last thing that happens.
Okay, but we haven't done replace it with a loop.
Oh, in this case, the compiler will automatically replace them, even in Scala. So in Scala will automatically do this when it can. And in Scala, there's some situations where it can't, but you can try this in Scala. If you take any old method and that you think can be optimized and write tailrec next to it, if it can't be optimized, then you get an error message. But so Scala will routinely, just any functional language, will routinely attempt to do tail recursion elimination because it's such a big saving. All right, more on Tuesday.